Okay, hi everybody. So, prove the convergence or divergence of the following series. Okay, so let's start with this one. Okay, so let c sub n be to the n over n squared. In other words, we're going to investigate these terms. So let's look at the ratios. Let's take the n plus first term divided by the nth and their absolute values. This is from the proof of the ratio test. And what is this? In this case, we get... Okay, so that's the numerator. Now I'll do the denominator. Okay, and careful manipulation of fractions. If this is not easy to you, spend some time thinking about this. There's one more 2 upstairs. This will stay downstairs. And this will go upstairs. Okay. If you want, we can expand, but we can already see what's going to happen. The limit as n goes to infinity of this new sequence, I have to find a sequence of ratios from this series, and the limit of this sequence of ratios is 2. Now remember, in the proof of the ratio test, somewhere there is the number 1, and then this number 2 is bigger than 1, strictly bigger than 1. Therefore, there exists some number r in between, and there will be a divergent geometric series that will build out of that r. I think it was like something like this, n equals 0 to infinity, and this will diverge because r is strictly bigger than 1. And then we'll be able to compare it to our series. And that was in the proof of the ratio test. But anyway, long story short, because of this limit being greater than 1, ratio test says that the original, not this sequence, but this series converges. Converges. This converges. We don't know what it converges to. We don't know what number it gives, but we do know that it converges by a comparison test with a... Okay, it diverges. It diverges. We compared it to... in the proof of the ratio test, we would compare it to a divergent geometric series. Diverges. Okay. Great. So let's do... That was this one. Let's do the next one. Okay, so now let's look at these terms of a series, but let's just look at, okay, so let c sub n equal 2i to the n divided by 3n square root of n. Okay, that's just these terms. Now let's look at a sequence that we define to be the sequence of ratios. And first of all, we're taking absolute value here. So, a -1 would go away, and also an I would go away. What do I mean by go away? The absolute value of I will be 1. Because where is I? In the complex plane, it is on the unit circle. And so the absolute value of I is 1. In other words, it goes away. So I'm just going to write 2 to the n plus 1 for 3 to the n plus 1 square root of n plus 1. Great, these are all positive, so I can just get rid of those absolute value signs, and it is still a true equality when I put the denominator. Okay, now let's get good at fractions. Okay, I believe that is correct. in which case the limit of the sequence of ratios of the terms of this series, this sequence converges to a limit, namely 2/3. This and this just becomes a 1, and the limit is 2/3. Oops. And here we are at geometric series, and here's 2/3 somewhere. And so there exists a number between 2/3 and 1, which is strictly less than 1, which will give us a convergent geometric series, and we will be able to compare it to our series. It'll be less than a convergent geometric series. This is from the proof of the ratio test. But anyway, ratio test says that the sum of the C sub n's converges since 2/3 is strictly less than 1. This converges. Okay, let's get another one. Give me some more room. Here we go. Let's look at these terms of this series. Okay, I was calling things C sub n. Why don't I call it Z sub n equals C to the n over n factorial for some fixed complex number. Okay, so let's define a sequence of ratios of absolute values. Okay, so what is this? Absolute value of C to the n plus 1 over n plus 1 factorial, and absolute value of C to the n over n factorial. Okay, so fractions, and these n's, they're positive integers, okay? So we can just pull them out of the absolute value signs and not be a problem. But this complex number, we'll have to sort of remember that it's really the absolute value of the complex number that will play a role. So let's see, we have n of them down here and n plus 1 up there. There will be 1 left over. And then there will be this. This is in the denominator, and this will come up into the numerator. And that is just some fraction stuff, so get good at that. Now, remember, n plus 1 times n minus 1 times n minus 2 times ... And then n factorial is really n times n minus 1 times n minus 2 times ... All these will cancel, leaving just an n plus 1 down there. Anyway, long story short, the absolute value of C over n plus 1. That is little a sub n. The limit of the a sub n's as n goes to infinity will be what? Well, the absolute value of a complex number, whatever complex number it is, let's imagine it's here. Okay, what's the absolute value of it? Well, it's just this positive or possibly 0 distance, this length. Okay. Well, no matter what that length is, as n goes to infinity, we're going to divide by a bigger number, and the limit of the a sub n's will be 0. 0 is strictly less than 1, so there will exist something here that will build a geometric series that will converge because it's less than 1, and we can compare. And that was all from the proof of the ratio test, and the long story short is that this implies that 0 is less than 1, so that implies that the ratio test says the sum of the C sub n's over n factorial, infinite sum, this series, is convergent, definitely, but it even says it's absolutely convergent. And really, I should have been saying that the whole time for any of the others that converged. Yeah, this one is absolutely convergent. Converges absolutely. Which means we can rearrange terms in the series if we wanted. In this series, we could rearrange if we wanted. This diverges, it doesn't diverge absolutely. That wasn't even something we defined. It just diverges. Just doesn't make sense. Okay, that's it.